Greetings, everyone. The work we're presenting today is a summary of the last 3 to 4 years researching industrial robots. My name is Víctor, and I come from Robotics, a robot cybersecurity startup. Together with me today is Federico Maggi from Trend Micro Research. The fun part about today's presentation is that it's being given by two researchers who went out of their way. I myself am a roboticist with about a decade of experience building robots who has, for the last few years, been researching robot cybersecurity. Federico is a cybersecurity guy who has been exploring robotics in the same way. We'll be presenting on behalf of all of our co-authors our work on reverse engineering industrial robots and the findings we encountered in the process. Let's dive into a small wonder. So robotics is the art of system integration. Building a robot requires one to carefully select components that exchange information across networks while meeting timing deadlines. Security in robotics is really nothing new if you've done stuff in IT and OT. It's a combination of both, a weird combination, let's say. There are a few aspects to consider, though. One relevant when compared to security is the fact that we in robotics make a strong distinction between real-time and real-fast. We use real-time as in traditional control theory. That is, real-time means deterministic, on time. Opposed to this, we have real-fast, which means fast, accelerated, or simply just low latency. We often found that real-time in some security domains refers to real-fast, so mixing them up, which is confusing. And this is important because, in a way, a robot is a network of networks, one that comprises sensors to perceive the world, actuators to produce a physical change on it, and then computational resources to process it all and coherently response in time, on real time. Of course, and according to its application. In the slide, on the right side of the slide, you can see a threat model for a robot manipulator, the one you can see also in the screen. Now, this robot, you can see, has multiple sensors, multiple actuators, and they are all exchanging information through different networks. Each one of these networks needs to be deterministic so that the overall control of the robot makes sense and the robot does what we expect. This control concept and determinism are critical and lead us to realize that security and safety are very, very connected in robotics. Safety cares about a robot not harming the environment or humans, whereas security deals with the opposite, deals with ensuring that the environment does not conflict with the robot's pre-programmed behavior. I think I speak on behalf of both to say that Federico and I are very, very pleased today to be presenting to an audience that understands the difference. But this is not what we've been finding over the last few years in the automation world. Robots have their own networks. They have their own technologies, safety requirements, and business priorities. And all of these must be uniquely addressed. Simply put, we can't secure robots the same way we secure IT or OT environments because existing industrial solutions for monitoring networking traffic often do not include robotics protocols. They do not include these specific technologies, and robots are typically left beyond the area of protection, assumed as air gap, or even in some cases, as some new solutions in cybersecurity are advertising, this so-called lockdown approach. This is far from the security we need in robotics. From a very technical angle, we demand robots demand their own specialized measures that take into account these safety characteristics, these safety aspects, so that robots can behave safely only if they are secure. And this is the exact topic we bring up in this slide as well. It's not just ourselves claiming this or many others out there, probably many of you as well. Norms themselves are saying so. If we take a look at the meta standard for functional safety, IEC 61508, we'll appreciate how there are several paragraphs that literally account for this and mention that if, as part of the risks that should be assessed, one identifies that security hazards could lead to safety ones, then one needs to conduct the proper assessments. Pen testing, threat modeling, things we've been doing in Alias Robotics for many years now in robotics. Now, something very interesting is that this leads to the fact that safety requirements spawn from security research. And this is huge for all of us. This is very important. This means that the CVEIDs you may get today in those robots in your kitchen, in your streets, in airports, wherever they are, those CVEIDs will need to be accounted for in the safety subsystems of all of those robots. Now, we started looking at industrial robots, as I said, about 4 years ago, approximately. And we put our target on these robots, which typically range from tens of thousands of US dollars up to a few hundreds of thousands. So sometimes very expensive. We cooperated with multiple vendors, some of the biggest ones we can say as of today. And one subcategory that caught our attention are the so-called collaborative robots. These robots are claimed to be designed to augment human capabilities by closely, and that means physically, cooperating without causing any harm. Now, the reality, though, is that past security research showed that there are vulnerabilities affecting this robot that even as of now, 2021, still remain unpatched. We refer to the work of IOActive with Cesar Cerrudo and a few other folks back in 2017, where they reported few vulnerabilities affecting these robots. And even as of today, they haven't been patched. So this definitely caught our attention. And we'd highlight that one of the biggest groups, particularly it seems following this trend of not caring as much as they should about security, is Teradyne. Teradyne is a big US company who has acquired different robotic companies, including Universal Robots and Mobile Industrial Robots. And we'll be speaking about this because these are collaborative robots that need to be essentially improved from a security angle. Now, besides cobots, besides collaborative robots, we also paid lots of attention to what seemed to be the first instances of obsolescence we observed in robotics. And the reality is that it's not uncommon for a robot to fail or to break down because, again, a robot is built out of many systems, a system of systems. And that means that one of these subsystems may fail over time, often leading to the complete system malfunction, given its interconnection with the rest of the overall behavior, right? So we got scared at the point where we realized that these very expensive industrial robots were not easily repairable. And this is what I guess most of you, as well as I did, would expect, because repairing these machines often is just about just replacing one component or even a part of the robot. I just want to grab the mechanics and just bring them up to speed with a new controller, and that saved me hundreds of thousands, for example. Well, contrary to my expectations and probably to some of yours, the reality is not this one. And similar to Ford in the 1920s with cars, most robot manufacturers oppose to this. They employ planned obsolescence practices, organizing dealers and system integrators into private networks, providing repair parts only to certified companies, and discouraging repairs, as well as evading competition. We fought this actively. We interfaced with some of these vendors. We reported responsively vulnerabilities. And after being ignored repeatedly, we decided we had to take a different approach. So we decided to empower the end users with the knowledge to protect themselves. And for that, we launched 2 weeks of robot packs. We launched these exercises in cooperation with other universities who contributed as well. And in total, we managed to publish more than 100 vulnerabilities altogether. It was a pretty successful exercise where we learned a lot. Particularly, we learned a lot about how to interface with some of these manufacturers. We'd like to share 3 main conclusions. The first one out of these exercises was that we definitely encourage security researchers to adopt disclosure deadlines of some form. We reckon that vulnerability disclosure is a two-way street, where both vendors and researchers must act responsibly. But the reality in robotics is that the safety hazards are such when connected to security that we definitely must pressure vendors to reduce the windows of opportunities that they give attackers by not mitigating all these flaws. A security-first approach in robotics is a must if we want to ensure safe robotic operations. The second bit, or the second lesson we learned the hard way, was that communication is extremely important and hard with robot manufacturers. Many of these manufacturers are trained in security and don't have yet the right, groups and qualifications. And as my old boss at Open Robotics used to say, Morgan Quickly, human APIs are the hardest. We experienced this first. So that's the second bit: be aware and careful when you interface with robot manufacturers. And the third one, which helps with the second one, at least it helped us with other manufacturers, is that essentially mediators help early in the conversations. They helped us very much down the road with the interfacing with more and more manufacturers, and they definitely will help you as well. Now, so let me share with you some of the actual experiences we've had over these last few years real quick. The first quote comes from Ole Storm. Ole is a very funny guy from Mobile Industrial Robots. He was the R&D manager at the time. And Ole, essentially to our concerns and reports, said that, well, their business model was just selling these robots to distributors. And literally, they didn't have control of these robots, and we had to go to distributors if we wanted these robots to be mitigated and more secure. We were shocked by this because he was literally telling us that these robots were not under control, and worse than that, they were shifting responsibility to their supply chains, to their distributors. So what we did obviously was we went ahead and we spoke with these distributors, and again we got shocked because these groups have had no idea about essentially the liabilities they were assuming, about the fact that they were in charge of essentially applying mitigations. Actually, even worse, many of these groups didn't even have the right training or security know-how to do so. So very concerning. And as you can see, these robots are not especially cheap. We kept digging, and eventually we spoke with Fernando Fandinho, the sales director of MIR, and Fernando finally told us, after asking many uncomfortable questions, that essentially we were not entitled to have access to the release notes. So even if we were to receive updates and or upgrades, which we never did, we essentially were not entitled to receive the release notes, which means literally we didn't know what updates were being applied, which says a lot about the transparency of this company. Now, take a look at the white robot, because that's the one that's being used here to build other robots, the so-called downstream manufacturers of robots. And this robot is the most popular robot used to fight COVID over these last few years, from UVD robots. We spoke with UVD quite a few months ago, more than a year ago, certainly. And we told them about our concerns. We told them and showed them how we could remotely take control of one of these robots. We could navigate it around a hospital, and we could even activate the ultraviolet lights, essentially causing potential concerns. To these concerns, to these thoughts, Simon told us that, well, the robot wasn't connected to the internet, so he didn't see how it could be externally hacked. Something, unfortunately, we are hearing more and more. Last but not least is Lars. Lars is the founder and CEO of Enable Robotics. And Lars just told us he was aware of the security issues, but that's about it. So obviously, we had to dive deeper. We had to take a step farther. And we did it by taking a step into teardown in robotics. Our motivations were threefold. First, we wanted to dissect and analyze these products to understand better the safety and security issues they were facing. Second, we wanted to have a way to do competitive benchmarking in robotics. This is really hard, even as of today. In robotics, teardown gives you that capability. And third, we wanted to gain the engineering experience that is required to serve customers and help them improve their robot architectures better. Federico is going to tell you more about the whys and the how.
Thank you very much, Victor. The reason that while we're here at Blackett is because we want to give you a loud message to both roboticists and cybersecurity folks. We would like you to start applying these techniques, these systematic teardown approaches to targets with the same passion, and I'm talking to the security community here, with the same passion that we put, for example, to reverse engineer a pure software artifact. Because there are so many targets, so many vendors, so many models and different variants that we really need systematic reverse engineering jobs to be published and documented. But we're fully aware that these targets might not be super easy to tackle. I still remember the way I felt when I first looked at, and this is only one component of a robot. I was like, okay, this is full of interesting things, but where do I get started? There are safety relays. There's a real-time OS in there with a computer with a dedicated CPU. There's a teach pendant out there. So it's really difficult for a pure software security person to even get started. Because at the end of the day, what you really want is to get more and more CVEs and hopefully inspire more fixes and have the blue teams develop good detection signatures. But yeah, if you're used to software reverse engineering, this is completely different. I think that the most striking difference is that, here you don't have any control Z, right? So if you look at this machine and you develop an exploit, then you really have to think for a long time before you actually deploy it, because one missing check, one wrong sign in an integer can really change the direction of the arm, and could really happen that, for example, the arm hits the container, and then you have to, I don't know, send the robot to maintenance for a few weeks, and that's a lot of time to wait for a security assessment. Let's now dig a little bit into the methodology. At the beginning, I think the good thing is that the scope of a teardown exercise is well contained into these cases, which are the robot controllers. You can see two examples on the left-hand side and in the middle from universal robots, which are pretty much the size of a suitcase. And on the right-hand side, you see an older generation of controllers for larger robots by ABB, those which work inside a cage. About tooling, I don't want to spend too much time. I just want to make you aware that, the manufacturers will not like probably what you're doing, so they're going to make your job a little harder. Make sure that you have all the tools that you need, including very exotic screwdrivers for all sorts of screw heads. And of course, yes, you're going to break the warranty. Make sure, very importantly, that you have enough space, but not just enough space for a single, one-shot engagement. Make sure that you have space that you can leave all the parts there for days or weeks, depends on how long you're going to take to find vulnerabilities. So make sure that you have a clean space for all the parts to be laid down. And then we go into the supply chain mapping step, which from my experience is the most fun part, because you get to learn all the parts used by different manufacturers. For example, here we'll learn that Universal Robot like to use power supply units from Artisan, and on the right hand side we learn that, understandably, ABB likes to use their own relays for the safety system, because they produce also relays and so on. So it takes lots of pictures to identify all the parts. And finally, if the engagement authorizes it, or if you are the owner of the robot, you can actually do the disassembling. And here, one note, you would like to take lots of pictures as well as short video clips, because you would like to bring the robot back into the same, assembled state, because you want to check your exploits if they work fine, unless, of course, you have a mirror unit. About the info gathering, you need three main things. Manuals, which are, I'm talking about technical manuals, which are relatively easy to find. Even if you don't own a robot, you might also start right now to use your favorite Google Docs, or have a look at that list of forums that I posted on the right hand side of the slide, to start finding technical documentation. Even if normally vendors do not make it easy to find, but there are plenty of material around. Second part, you're going to need so-called OLP, or simulation software, and that's your Control Z, because of course here it's all simulated, so you have all the peace of mind to try all your exploits and then test the robot, get familiar with the programming language. And if you're curious, you can check my Black Hat talk from last year, where we got you through all the ecosystems of the main manufacturers. And finally, of course, you want the operating system image, but I warn you, this is not going to be easy to find unless you have a target at hand. Right, now let's take a look at the three main case studies that have been performed on three different targets. Here you see in a larger image the controller of a universal robot, and on the left-hand side the teach pendant, which is also another interesting target. It's usually a tablet, a RUG tablet, so to speak, with its own operating system. The fact that we don't find the key, in this case there is the key right there, but if we don't find the key to open the cage, I think it's a good sign, because it means that whoever deployed that robot has given some thoughts about physical attacks, which are, as Victor will show you later, a very easy but also very effective way to target these machines. Then we open the cage and we find out about the safety system. And if we look carefully, we can identify the MCU. So it means that the safety system here is running in software. So engaging and disengaging the safety relays is a software decision. It's not something that is only electrically driven. And then we can identify the MCU, and we can take a look at the documentation from the manufacturer of the CPU, of the MCU, and we find out that, well, at the first glance, it looks like it's a good choice because it's usable, it's useful, and meant for industrial automation. But if we dig carefully in the data sheet, we find out that the manufacturer of the chip, NXP Semiconductors, warrants against the use of this in safety or life-critical conditions, life-critical systems. But unfortunately, this is the safety system, not just the LED driver or anything else of a robot, is the safety system of a robot, which decides whether or not a collaborative robot in this case must stop the motors or not because there is an endangering condition. In the second generation of the same series, we have found out that the manufacturer have made a step forward in the right direction, we believe, because instead of using an MCU with a firmware, they have used an FPGA, which gives you near hardware performance in terms of engaging and disengaging relays when it's needed. So we think it's a step forward. What we think it's actually a step backward is the fact that, as Victor anticipated, even though the two components, the controller and the robot of the two different generations, are completely compatible from an electrical and mechanical point of view, and you can see that they're almost overlapping, they have changed the shape of the connector. So if you own an older generation controller and a newer generation ARM, and you want to use them together, you cannot unless you build a proper adapter. So we think it's a step backward into somehow trying to break the backward compatibility. A third case I would just want to highlight very briefly, another interesting target for security researchers, which you might not think of, that a simple component such as a motor driver contains a firmware itself. And if we look at once again at the safety disclaimer put there by the vendor, we learn that dangerous uncontrolled motor runaway conditions can occur for a number of reasons, of course, including faulty firmware. And if you're curious, you can download the firmware from the vendor's website, which I think it's an interesting thing to put your hands on. And now I want to hand it back to Victor, which will show you how this works in concrete and what is the outcome of this approach applied systematically over several years. Victor, the floor is yours.
Thank you, Federico. That was awesome. So as he pointed out, let's now take a look at the results we obtained. The previous case studies Federico highlighted essentially show how robot teardown is relevant for quality and safety inspection, as well as cybersecurity research overall. Throughout these 4 years, we found more than 100 security flaws, and 17 out of these were assigned new CVE IDs. Unfortunately, those 17 still remain as 0 days today. All this data is actually publicly available and disclosed. We pushed it to the Robot Vulnerability Database, RVD, which is a project that's partially funded by the European Union. You've got a link over there, and we encourage you to check it out, to support, to help maintain it, and to use it as a resource to also do your own research. Now, let us dive now into some of the examples that we POC'd for illustrating these findings we had. The first one on the left side of the slide shows how essentially we managed to, by exploiting one of these vulnerabilities, compromise the robot and particularly compromise its safety subsystem. By disabling it, we can see how the robot, instead of stopping when it detects an obstacle, it collides directly against it. Now, imagine this same reality, this same situation in a hospital with a robot carrying relevant payloads such as blood or utensils for surgery, whatever. This is happening, and unfortunately, these robots are vulnerable. The one on the right side shows a bit of a more complicated attack. In here, we are using different vulnerabilities, and the attacker would need to have certain knowledge of the robotic system, because it requires the attacker to essentially mess up with the computational graph. The computational graph in the robot is the brain, in simple terms. And this graph essentially is in charge of the behavior overall of the robot. Messing up with the graph means you can really make the robot do whatever you want. This, of course, includes also extract or exfiltrate the information you want. That's exactly what we are showing in here. After pivoting through different subsystems, we reach the main computer, we access the computational graph, and particularly we extract the information that comes out of the localization modules. We extract the map that's being constructed, and we can see that realistically. Of course, we could also access camera images and other information that's being perceived by the robot. This third example shows you an instance of ransomware in a collaborative robot, the robots from Universal Robots, also owned by teardown. In this case, we're using a physical attack vector to illustrate how easy it is to compromise such a robot, literally encrypting the file system, disabling the safety mechanisms, and of course, asking for a ransom. Now, we are demonstrating it here with a physical attack vector, but the same exact thing can be done via network attacks. We can do it through local networks or even adjacent networks. And many of these robots are unfortunately connected directly to the internet. So definitely concerning, and definitely something we need to work against, which led us to share with you our thoughts on this, which point towards the direction that we should really be very careful about which robots we place our trust in, and we should take security very, very seriously immediately. As Federico pointed out, we appreciated certain changes in the electronics of these collaborative robots across different versions, across older and newer versions. But we found no real reason why backwards compatibility should be an issue between these robotic arms. This would mean essentially that customers with an older version of the robotic arm could repair or reuse the mechanics and bring it up to speed with the new controller, which may or may not add new capabilities without being forced to pay a premium price. And we are speaking about tens of thousands of US dollars, and in some cases, much, much more than that. Unsurprisingly, we observed that the manufacturer introduced subtle changes meant to make this particular intent harder, which we can only justify as what appears to be attempts to exercise obsolescence practices. Another of such actions includes the obscurity we observed around the changes introduced with newer versions of the robots. Particularly, these changes can be summarized as adding an extra sensor, a 6-axis force torque sensor at the tip of the robot to gain additional sensing capabilities for smoother behaviors and new behaviors overall. Now, the exact same thing can be done in the older version of the robot. And the lack of transparency, once again, will impact end users and will make them or force many of them to buy complete new sets, again, spending many, many, many resources in a very much unneeded manner. So, of course, we dived deeper. We wanted to at least POC a way to bypass these obsolescence practices, and we developed 2 prototypes. The first one, which we named Controller Adapter, allowed us to electrically interoperate older and newer versions, exchanging controllers with mechanics and so on, the other way around as well. This took us essentially just some crafty mechanical component with electrical matching connectors for a total bill of materials of under $20 US. So pretty simple fix and pretty useful, we believe. The second prototype we made was called ARM Adapter, and we used a Raspberry Pi to interface with the communication signals at the tip of the robot, giving us the capability to drive the robot around without the need of an actual controller. Of course, we discouraged the use of such an approach in production because we removed completely many of the safety considerations. However, with this, we demonstrated how teardown empowered research to extend the robot capabilities and bypass some of the obsolescence practices and limitations we have observed. Now, we don't have time to go through all of these quotes, unfortunately, which we observed while cooperating with many manufacturers these last few years, but I'd like to at least stress the last one, which really kind of like got into our hearts, because we once heard from pretty big manufacturer that they literally thought that robot cybersecurity was up to the end user. Of course, we oppose to this statement, but the reality is even worse. It's not just that this is not true. It is that cybersecurity today is up to the hacker. Robots are so insecure that it's really up to any attacker to come up with the right exploit, which is very, very easy most of the times, and disrupt industrial operations. So three last sound bites to try to encourage more proactive research and mitigations. The first one, please note that robots are only safe if secure. Second one, teardowns are very much needed for security research in robotics. And we should all together put pressure on manufacturers to reduce how much time they take to provide mitigations. Third and last but not least, we definitely need a right for repair in robotics. One that allows us to fight actively these planned obsolescence practices, and one that allows us to design and come up with better robotic architectures. We hope you enjoyed our small wonder journey. We certainly did. Would like to thank our co-authors, all of them. It was awesome to work with you, and thank you so much for all of your effort. Thanks also to University of Klagenfurt, and to those of you who want to learn more. There is a white paper we are publishing, which you can go ahead and read if you'd like to learn more. And other than that, we're open for questions. Thank you so much for your time.